Good morning, students. Today our topic is neutron and its properties, how the neutron is discovered and their properties have to be explained here. This is one of the unit in thermodynamics, electromagnetism and modern physics. So here, this is the topic neutron discovery and its properties. First of all, we are going to see about that modern atomic theory. Here, we are taking a matter is consisting of atoms. The atom cannot be created or destroyed, and also it cannot be subdivided in ordinary chemical reactions. These changes that atom creations and destroy can occur in nuclear reactions only. Atoms of an element have a characteristic average mass which is unique to each element. Atom of any one element differ from properties of atom of another element, so that each atom have different properties, and also the atomic mass is unique for each element. So these are the conclusions which are derived from the study of an electron. First of all, that electron is discovered. So in that discovery of electrons, that cathode rays are used. The cathode rays have the properties like an electron. So all elements must contain identically charged electrons. Here, the atoms are neutral, so it must have positively charged particle and negatively charged electrons. Both are balanced with each other. That electrons have little mass such that that atom must contain other particle than that of most of the mass, so that the neutron occupy small space only. So most of the mass is occupied by other space, that is called as the positive particles. Next is that Thomson atom model. So in the Thomson atom model, he believed that electrons are like a lumps embedded in a positively charged footing. So it is called as plum pudding model. So in this, here there will be a positive footing is there. Inside, electrons are distributed so that matter model has some defects, because it, from the previous conclusion that number of atoms and the number of positive charges and negative charges balance with each other. So it is not exist in that Thomson atom model. Then after that, Rutherford came and he did an experiment. That experiment is called as Rutherford gold foil experiment. In this, there is a nuclei of helium is taken. This will emit alpha particles. The particles are fired at a thin sheet of gold foil. The gold foil is kept inside the detecting screen. So in that detecting screen, there is a slit is there through which alpha particle passed through it. So while the alpha particle incident on the gold foil, some of the alpha particle penetrate through that gold foil and some are deflected on the same path. Here, from this, some conclusions are made by Rutherford. So here, most of the particles passed right through the gold foil. Few particles only deflected. Some of that particles are greatly deflected. So from this, Rutherford came on a conclusion that the nucleus is small and it is a dense one and the nucleus is positively charged. So these are the conclusions made by Rutherford. So we conclude from the Bohr atom model that nucleus is at the center of the atom. Around this, the electrons are revolving around this. So, beyond this, there is another particle is there. So that is called as neutron. Here, the neutron is a subatomic particle which has no electric charge. The neutrons are usually bound in atomic nuclei. So, nuclei of each atom consist of protons and neutrons. So, that protons and neutrons both are known as nucleons. Here, the number of protons determine the element. Here, the number of neutrons determine the isotope. Here, isotope means the isotopes are atoms of the same element which is having same atomic number but different mass number. The different mass number is due to the different number of neutrons. Here, for an example, nitrogen, here there are two isotopes will be there. One is N15, another one is N14. So here that atomic number of nitrogen is 7, so that for the first one the number of neutrons is 8 For the second one, the number of neutrons is 7. So that here the number of neutrons are varied. So it is a isotope of nitrogen. So to find out that neutron, the preliminary experiments are done by Pothier and Becker in the year of 1930. So, according to their experiment, there is a particle which is having some properties like penetrating non-ionization radiations when it is pumped from beryllium compartment. So these radiations are called as gamma rays. After that, that rays are exposed in paraffin. So here we are we are getting high speed proton ejected from the surface of the paraffin. So this results recoils interpreted as the Compton scattering. So that discovery of neutron is concluded as the electromagnetic radiations are called as gamma rays. So which is having energies in the order of million electron volt. Here, Curie and Juliet performed several measurements to study the penetrating high energy gamma rays. In the year of 1932, Sharpick proposed that the new radiations produced when alpha particle incident on beryllium is consisting of neutrons. The experimental data estimated the neutron mass as between 0.1.005 Armstrong unit and 1.008 Armstrong unit. So this is the experimental setup for the discovery of the neutron. Here it is having a vessel which is having polonium source and beryllium target. There will be a ionization chamber that is connected to a amplifier and a oscillograph. So next is that here in that discovery of neutron, Rutherford proposed the atomic structure which is having the massive nucleus as nuclei of an atom. So after that in 1932, scientists to know which the particles compose in that nuclei, some other particles are inside the nuclei. So why they conclude that means due to the nuclear size. By using the uncertainty principle, that uncertainty principle is that no two electron can have all the quantum numbers is the same. By using this principle, here uncertainty principle puts a lower limit on kinetic energy. The kinetic energy is much larger than the kinetic energy absorbed for electron, emitter from the nuclei. Then next one is that nuclear spin. That if a neutron, this will be the isotope of hydrogen, and the neutron consisting of protons and electrons. The neutron must contain two protons and one electron, so that the nuclei composed of three fermions, which result in a half integral spin. But it has been measured to be 1. The next one is that nuclear magnetic moment. The magnetic moment of an electron is 1000 times larger than that of a proton. So the measured nuclear magnetic moments are on same order of magnitude as that of the proton. By the invention and the experiments of Bothy and Becker, the radioactive polonium source emitted the alpha particles. When these alpha particles bombard the source of beryllium, the radiations are penetrate through the beryllium up to several centimeters of lead foil. After it is passed through the lead foil, so that gamma rays are emitted from that source, that is passed through the paraffin wax. So after that, here in the paraffin wax, the protons are displaced by neutrons. So that the invention of neutron is discovered by Chadwick by using the previous experiment. The nuclear properties of the atomic nucleus is defined as XAZ. Here, A is the mass number, Z is the atomic number, N is the number of neutrons, X is the symbol of the atomic nuclei. So here, that atomic number characterizes a chemical element. The dependence of chemical properties on neutron numbers is negligible. So, nuclide with same neutron number are called as isotopes, and same value of A are called as isobars. The nuclear properties are explained here. Here, all that mass is explained by the symbol U. So 1 U, that is 1 atomic mass unit, equal to 1.66054 into 10 to the power minus 27 kilogram. So it will be converted into million electron volt, that is 931 million electron volt per C square. For proton, it is denoted by the symbol P, and that rest mass energy is 938.2 million electron volt. And this is same for that, is most probably same for that neutron, that is 939.566. The charge of proton is plus E, but for neutron there is no charge, so the charge is equal to 0. The mass of the proton is 1.0072765, and for neutron is most probably same as that proton. The spin of proton and neutron both are same, that is half only. And for electron, it is denoted by the symbol E. The electrons are revolving around the nucleus, so that it is having the rest mass energy as 0.51100. Then the charge of electron is minus E. Here the mass is equal to 5.4858 into 10 to the power minus 4. So it is the mass is very small compared to the mass of the proton and neutron. Here the proton and neutrons collectively called as the nucleons. This is that instability of the free electron and mass. The free electrons are unstable, so that they undergo beta decay, and the lifetime is 885.7 plus or minus zero point 0.8 seconds. That neutrons cannot be stored for a long time as free. That neutrons are disintegrated into a proton, electron plus another particle. That mass is slightly larger than that of the proton. So already it is shown in the previous slide. And also the neutrons have a spin. Both proton, electron and neutron are having the half spin. S is equal to half. That angular momentum is equal to root of S into S plus 1 H cross. And these particles have the angular momentum, which is explained by the magnetic moment. So that magnetic moment is equal to G into Q by 2m into S. That electrons also have the same spin, that also explained in that previous slides. So these are the properties of neutron. The neutrons has both particle-like and wave-like properties. The charge of neutrons equal to 0. The spin is half. The mass of neutron is 1.675 into 10 to the power minus 27 kilogram. The magnetic dipole moment is that minus 1.913 millinewton. So here nuclear magnetron is explained as 5.051 into 10 to the power minus 27. So the velocity, kinetic energy, wave vector, wavelength, temperature, everything has to be calculated for the neutron. So these are the sources of neutron. First of all, that is continuous reactors, then spallation sources, pulsed reactors, and photo neutron sources. These are the different types of neutron sources. So that nuclear reactor. So in this nuclear reactors, the neutrons are very useful here. So the nuclear reactors are based on the principle of fission. Here we are using heavy elements like uranium 235. So while fission of uranium 235 yields 3 or 4 neutrons per fusion, per fission at 2 million electron volt kinetic energies. Here, in that nuclear reactors, we are using moderators. So that will be used to slow down the neutrons to thermal energies. And also, the nuclear reactors are having reflectors that are used to maintain the core critical, whereas the electrical power producing reactors use wide core sizes and low fuel enrichment. So here uranium 235 in this 2 to 3 percentage uranium 235 is there. So these research reactors use compact cores and highly enriched fuel in order to achieve high neutron influences that regulatory agencies encourage the use of intermediate enrichment fuel in order to avoid proliferations of weapon grade material. So, in that moderators we are using in nuclear reactors. So here we are using the principle of the light nuclei plus low absorption. So here there will be a elastic collision between the nucleus and the neutron so that the nucleus transfer the energy to the nucleon. So after the elastic collisions, there is no change in that energy. Here, the moderated neutrons take up that average kinetic energy and set its by T. Here, the next topic is neutron scattering. The scattering of neutron occur in two ways. One is through interaction with the nucleus, and second one is through interaction of unpaired electrons. So that tends magnetic moment with that magnetic moment of that neutrons. So here the magnetic moment of electron and the magnetic moment of an electron is compared. So here the incident waves incident on that nuclei. So here it is scattered by the nuclei. So here there will be a interaction of unpaired electrons with that magnetic moment of that neutron. So other thing is that coherent scattering. How that scattering takes place while the incident particle on that nucleus. So here, first of all, coherent scattering. So this will occur when there is a phase relationship among the scattered neutrons. This represents that the scattering can produce interference and it will provide the structural information of the nuclei. Next one is that incoherent scattering. So in that incoherent scattering, the scattered neutrons do not have phase relationship. So this will happen because of the difference in scattering length of the different elements, even in different isotopes of the same element. So different isotopes of the same element have different magnetic ordering, and this will leads to the different scattering length. Here, this is the summary of various techniques of neutron scattering to determine the various aspects of matter. That scattering is divided into two types. One is elastic scattering, another one is the inelastic scattering. So, in elastic and inelastic scattering, there are two types will be there. One is coherent and incoherence. That coherent structure determines the equilibrium structure. The incoherent structure gives the unwanted background. For that, inelastic coherent scattering determines the dynamics of the material, and inelastic incoherent scattering gives that atomic diffusion. So this is the one of small angle neutron scattering. So this is used to study the structure on a scale length of 10 to 1000 Armstrong unit. By using that, we can find that structure of a material, most probably nanomaterial structure, can be explained by using that small angle neutron scattering. So these are the components of neutron scattering equipments. So first of all, monochromators. So that is used to analyze the energy of the electron beam by using the Bragg's law. So next one is that collimators. It defines the direction of travel of a neutron, and there is a guides are available that is used to allow the neutrons to travel large distances without suffering intensity loss. And also there is some detectors are available. The neutron is absorbed by helium, and the gas ionization caused by recoiling particles are detected by the detectors. And also here choppers are available that is used to define the short pulse or pick out a small band neutron energies. There will be a spin turn coils are available that is used to manipulate that neutron spin using Lamer precision, and there will be a shielding is available. This is used to minimize the background and radiation exposure to the users. So these are the advantages and disadvantages of small angle neutron scattering. That advantages by neutron scattering lengths vary randomly with atomic number, but in that wide range of wavelength can be achieved by using the full sources. As far as information through the nuclear reaction, the signal to noise ratio is the highest one. In the terms of disadvantages, for small angle neutron scattering, we have to install the system, and more cost will be there for the maintenance. Here, the neutron sources are characterized by large flux and have limited use in investigation of rapid time dependent processes. Large amount of sample is required for that small angle neutron scattering process. So, we conclude that the atomic particle consisting of three type of particles. One is electron, proton, and neutron. So, the charge is different, but for neutron, the charge is equal to zero. It is a chargeless particle. So the atomic number is that number of protons and the number of electrons. So both are same, that is equal to a atomic number. So that mass number is that number of protons and number of plus number of neutrons. So here for different atoms, the proton number, neutron number and the electron number has to be calculated. Next is that isotopes. Already the neutron number decides the isotopes. That isotopes are atoms of the same element that but it is having different mass number. For hydrogen, there are two types of isotopes are available that are deuterium and dilithium. So in this, the proton or electron numbers are same, but neutron number is varying. From this, it is concluded that this is a isotope. So atomic mass is that average of all naturally occurring isotopes of that an element. So here that carbon 12 isotopes, so it is made up of 6 protons and 6 neutrons. But for isotopes like carbon 13 and carbon 14, the number of neutrons only varying. But carbon 12 exists in nature with a large quantity. But for other isotopes, they are not abundant in nature. So we can compare that X-rays and the neutron. First of all, we must know about how that X-rays are produced. When that radiations incident electrons are incident on the metals, X-rays are emitted from the surface of the metal. That is called as that X-rays. The X-rays are scattered from the electron cloud surrounding by the atoms. Okay, so that electron incident on the metal target, it excites that atoms in that atom cloud. So the neutrons scattered from the atomic nuclei influenced by neutron nuclear force. So that X-rays and the neutrons are compared with each other by here, that X-ray cross-section and the neutron cross-sections are compared. Here for hydrogen, lithium, carbon, that is by increasing that atomic number, that X-ray cross-sections also increased. But for that neutron cross-sections, it is not like that. For hydrogen and zirconium and carbon, it is having that high neutron cross sections. For others, it will be varying. There is not a gradual increase in that X-rays cross section or neutron cross section. Here, that wavelength of a neutron is in that range of 10 to the power minus 10 meter. So this is for neutrons and for that X-rays. X-rays are scatter from the electron cloud. The electron cloud is on the surface of the metal target. The electrons scatter from the atomic nuclei. So the nuclei are Wien scatters with respect to lambda. So these are that some points about that neutron discovery and neutron properties, and also that neutrons uses in different area, and how that X-rays and neutrons are compared with each other. So these are explained in that. So these are that some points about the neutron discovery and their uses. Thank you for listening.